Hello friends, welcome. I'm Powell and today we are going to be looking at the first part of first set of questions under the kinematic series. So let's begin. The first question says the magnitude of the acceleration of an object moving along a straight line is equal to there. So we have four options. Which of these options is actually the correct option? So let's look. A, they say the slope of its displacement time graph. Here we're talking of the acceleration of an object moving along a straight line is equal to the slope of its displacement time graph. Okay, we don't know. B, area below its force time graph. C, slope of its velocity time graph. And D, area under its velocity time graph. Okay, so let's see which of these options makes sense. Correct sense, actually. Yeah, like the best sense. Okay, so our answer is C. And now this is an illustration of a velocity time graph where we have an object moving along a straight line. Yeah, that means the acceleration of an object. So of an object moving. So in this case, you can see that the slope here is equal to the velocity all over the time. And from our knowledge in mechanics, calculus, we know that this is equal to the acceleration. Yeah, in this case, A is the magnitude of the acceleration. And here, okay, if you want to take the slope of this curve, where we have the change in y all over the change in x, or let me see, at the change in the velocity axis all over the change in the time axis, we have, okay, let's just call that change here v and here t, even though this is just let me just say an expression here. So in this case, we see this slope here as v on t, and that is the slope of its velocity time graph, giving us A from our basic knowledge of mechanics, yeah, kinematics, calculus. So we see how and why the answer C of the slope of its velocity time graph, yeah, is equal to the slope of its velocity time graph. Yeah, thank you very much. So let's move to the next question. Okay, next question says, which of the following is true for a body moving in a circular path at constant speed? Which of the following is true for a body moving in a circular path at constant speed? Okay, let's see. The acceleration is perpendicular to the velocity. Okay, we don't know yet. Let's just continue. The acceleration is constant with time. Okay, let's move on. The acceleration is always directed opposite to the displacement. Should we say, well, let's just move on. The centripetal force is provided by the weight of the object. That sounded like, yeah, it makes sense, but let's see which of them makes sense. Okay. So, answer here is A. The acceleration is perpendicular to the velocity. That means this is true for a body moving in a circular path at constant speed. Okay, let's picture this out. You have this body moving around the circular path, and here you have its velocity. Sorry, I didn't put it like an object, like a point object. Oh yeah, point mass, point object. It actually needs to be like point object. Sorry for that. So we have this velocity here moving towards this direction, and you have the acceleration moving towards the center, and this acceleration is often called the centripetal acceleration. So you see the acceleration is perpendicular to the velocity. And let's get some little explanation on this. When a body moves in a circular path at a constant speed, its velocity is constantly changing because the direction of the velocity vector is changing. You understand, right? The speed is constant, but the direction changes. And velocity is you're considering the speed, but with respect to direction, making it a vector quantity, not longer a scalar, because speed just deals with the magnitude, but the vector includes the direction. So as it's moving around this circle, even though the speed is constant, but the velocity changes. So its velocity is constantly changing because the direction of the velocity vector is changing. Acceleration is the rate of change of velocity. And in the case of circular motion, it is directed towards the center of the circle. And like I said, well, in mechanics, you have circular motion, and you get to picture out that this is called the centripetal acceleration. Okay, so let's move to the next question. Wow. Third. Okay, so our third question here says a ball is thrown vertically upwards so that it returns to the thrower. We hope it doesn't hit his head. The value of the acceleration of the ball at the highest point reached is imagine yourself, you throw your ball up. Just imagine yourself throwing this cupcake. Here we call it gâteau, or yeah, we have a name called pop like they have the native one we do here. So when you throw it up and then it reaches the highest point. You can call it the maximum height for people maybe used with calculus. Or yeah, you should be. Even if you are not, it's okay. You're learning. You're coming up. I mean, I was like, what's all these when I was coming up? So, but I got to know it. So the highest point, what is the acceleration at this highest point? Imagine it flies and you see it stopping somewhere and then it goes up, stops somewhere and it comes back. So at that point, what actually happens? You might be say, okay, it stops. So since it stops there, let's say its speed at that point is 0. So okay, there's no change in speed. It's not circular motion. Therefore, it's not accelerating. Okay, you might be tempted to, you might want to say that with that assumption, but let's picture this out. You are standing on Earth, right? And you know all bodies, no matter where you stand, if you're given a possibility to fall, you're going to obey G. You're going to obey G. That's 9 point. Let's just consider it's 9.81 meters per second squared. And at that point, even though its speed is 0, but what is its acceleration at that highest point? We are going to consider it to respect G still. So it's going to be 9.8 meters per second downward. Okay, so you see, right? So I explained that, and so this C might be tempting if you consider the first case, and you'll be like, okay, oh yeah, or maybe if you are not often used to with solving physics problems detailedly, you might maybe coming from can I say kindergarten or normal secondary school, and you've been using 10 and like okay, you'd have just been maybe scared of you using decimal places and you're tempted to take this answer. Okay, so let's move on. Let's move on. Okay, so we are now on the fourth question. The fourth question says, which of the following statements is correct? Which of the following statements is correct? Okay, here we go. It is possible for the speed of a body to change without the body accelerating. I don't know. I don't know for now. It is possible for the velocity of a body to change with a change in speed. Does this look familiar? I don't know. For now, it is possible for a body to be accelerating while traveling at constant speed. Does this look familiar? I don't know. It is possible for a body to be moving with resultant force acting on it. Resultant force, mechanics, that law, like all these things just coming blowing up in your mind, and you're like, oh, okay, like I think I got the answer. Let's see. Not so fast. Okay, so here, answer B and C actually are correct statements. B is correct. What is B? It is possible for the velocity of a body to change with a change in speed. I think we saw this earlier, right? B is correct as the velocity can be changed with a change in speed. Yes, or the direction of motion. Good. The change in speed can cause change in velocity, like actually, can I just say, or the direction of motion? Yeah, change in speed actually affects the change in the velocity, and that is in the terms of it being a vector. That means it's depending on the magnitude and also on the direction of motion, or both, right? Either of them. Now let's see for the C part why it is correct. It is possible for a body to be accelerating while traveling at constant speed. For C, such a situation can be seen in circular motion. Mm. Okay, you can understand that, right? It's possible for a body to be accelerating while traveling at a constant speed. Like we saw in the other example. I think this is almost in the same example. We kind of had this little remembrance. You see this body moving around with constant speed, and as it's moving around with a constant speed, the velocity is changing. The velocity is changing, like, because the ball is moving in different direction, and this velocity changes. And as the velocity is changing, okay, so do we expect a change in acceleration? Okay, it's quite deep. Okay, so that's why we have a B and C. But even though I think actually the best answer to this question, I think, should be B, if in case you are asked for one, because this year I have a little bit of okay. Okay, so let's move. Oh, yeah, like, okay, let's be like, oh, is the feet pushing already we are moving towards? Let's see. Oh no, physics. We don't want to go first. We want to enjoy you. Yeah, it's a wonderful, wonderful system created by God. Everything just went perfect. Okay, question 5. A person jumps from a height of 1 meter. Oh, I was imagining kind of someone jumping from a very high distance, but it still makes sense. After all, if you put some of us to jump some, even half a meter, we'll be scared, right? Maybe the ladies with high heels, and lands stiff-legged on bare ground. The person's mass is 60 kilogram, and he is traveling at a velocity of 45 meters per second. Just prior to hitting the ground. If the person takes 0.05 seconds to land, the force developed will be tin 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 tin. Do you want to be a millionaire? No, this is not a millionaire competition. Okay, so A 5,400. 5,400. You want to hear that? Okay, was that what I wanted to say? 5,400 Newton. B, what do we have here? 54,000 Newton. And C, okay, 540 Newton. D, negative 5,400 Newton. But are you that, like, these values, you just arrange them in your head to just give you the right answer? Okay, not so fast. Let's look at it mathematically. Like, yeah, let's take it at a time, right? Yeah, once at a time. So, okay, so here is still a question. Don't mind the way the environment just changed. We are still here. Okay, so this is the same question, and we haven't the solving. The answer is B, 54,000 Newton. But how? Let's see how we approach such a question. So let's look at the question again keenly. A person jumps from a height of 1 meter and lands stiff-legged on bare ground. A person's mass is 60 kilogram and he is traveling at a velocity of 45 meters per second just prior to hitting the ground. If the person takes 0.05 seconds to land, the force developed will be so if you understand the equation and you have this person like falling on the ground, you have his mass and they give you the velocity at which he was traveling, and then he see him hitting the ground, like we talk of him just he actually hits the ground. Okay, and then but before hitting the ground, if the person takes 0.05 seconds to land, the force developed will be okay. So we have now we need to what we have. Okay, this is what we have. We understand it. Okay, we have like colliding something colliding, and then our mind just comes towards like momentum, impulse, and the whole show. So that is how you kind of somehow it helps you to picture our problems when you get some of these little um things like you hear of colliding, you hear of hitting, and all this maybe like momentum just comes to your mind. So let's move. Okay, to calculate the mass developed when the person lands, we can use the impulse momentum principle. The impulse is defined as the change in momentum of an object, right? The equation for impulse is force times time. Impulse equals force times time, and momentum is equals to mass times velocity. So the person's initial momentum is initial momentum, the mass times the initial velocity. So we know the mass actually. Sorry, I didn't collect the data to place it somewhere, but we can view it from here. The person's mass is 60 kilogram and his initial velocity is 45 meters per second. So when we actually carry out this multiplication, we have 2,700 kilograms meters per second. Now, at the moment of landing, the person's velocity becomes zero, right? Like when he lands, his velocity becomes zero. So the final momentum is zero. You understand, right? Because his final momentum is actually his mass times his final velocity. And if his final velocity is zero, so you have his mass 60 times zero, which will give you zero. Now, the change in momentum is actually the final momentum minus the initial momentum. But what is the change in momentum here in terms of when we're working with numbers? We know our final momentum is zero and our initial momentum is what? 2,700 kilogram meters per second. So we have the zero minus this, and it gives us this negative value. But that's just a change in momentum. What we are asked is the force developed. So let's not just like, hooray, we got the answer. No, no, no. Let's see. Okay, so using the impulse momentum principle, impulse is equals to the change in momentum. We know that. So, and we know the force times the time. This was our change in momentum. But our change in momentum was this value. But we don't want to look at this value now like as like only as a change in momentum. We know that impulse is force times time. So if impulse is force times time and impulse is equals to the change in momentum, so this our change in momentum, which was negative, and which is negative 2,700, can be equated to the formula for impulse, which is force times time, right? And now if it can be equated to the formula for impulse, which is force times time. Let me explain again. Our change in momentum is negative 2,700 kilograms meters per second. And our impulse from our previous slide gave us that you can go by and view it. We saw that it was force times time. So since we know that using the impulse momentum principle, and we know that the definition of impulse is that impulse is a change in momentum. So we can take this value for change in momentum we had in the previous slide, which gave us negative 2,700 kilograms meters per second, and we equate it to the formula for impulse. And what is the formula for impulse? Force times time. And that is what has been done here. So we want the force, right? Because it's asking us the force developed, right? The force developed will be, so we take this time and we send it over to this other side of the equation, right? In other words, we just divide all through. That means this side and this side by time. You divide here by time, and if you're dividing here by time, time cancel this time. If you're dividing under this 27 by time, you just have this 2,700 by time, you just have it over time. So that's what has been done here. But we just say in a in a in an area, we just say you send this time the other way, and that's just a way to escape some explanations. Okay, so here we have these, and so we input our value for time under here, and this is our value for time, 0.05 second, and this is where it was gotten from. If the person takes this to land, so we attach this time under here and take this negative 2,700 kilograms meters per second, and we divide it by our time, which is 0.05 second. So using your calculator, we're going to, or if you can compute it with your mind, okay. Sometimes it's just good for you to be able to carry out this manually. It helps you improve your problem thinking and skills and rest. So you have your force now to be, after computing this, your force gives you 54,000 Newton. Sorry, negative 54,000 Newton. Now, if your force has given you negative 54,000 Newton, and here they just ask, the force developed will be, so what comes to your mind? They just ask you for the force. They didn't ask you for the force and the direction, right? Just ask you the force. They didn't ask you if it's coming down or if it's going up. So, however, the equation is asking the force developed, which is the magnitude, right? The magnitude, meaning that you just give the value without a negative sign. Even if it's positive, you just give it to the positive value still. I repeat, even if the value is positive, you just give the positive value still, but if it's negative, you remove the negative sign. So, which is the magnitude bracket non-negative sign of the force, which is magnitude of the force. Therefore, the answer is 54,000 Newton. So B is, yeah, which is our answer, 54,000 Newton, taking the magnitude of the force. Yeah, so okay, so now I just have one thing to say to you. God, please, our Lord Jesus Christ, bless you. Amen.